Swayam Prabha. Digital India. Educated India.
Good morning everybody and welcome to our course on Introduction to Micromechanical Machining. In the last class we have seen some of the aspect of the error in the machining processes, and we have seen that there are no any component which are very perfect. So, we have to identify or we have to put some criteria so that we can accept a particular part. So, we have seen different criteria. First one was the tolerance, by which you can actually accept or reject the component. If the dimension you want at 10 millimeter, if it is within the 10.24 or 9 point something, then you can accept the part. Another thing was the roughness. If roughness is acceptable within a particular range, then you can accept that component. Third one was the shape, because if there is a shape deformation is there, that means if you want a perfect sphere and it is little bit deviated out of that sphere, then you can reject that part. And another one was the property related to the material. If you are functionalizing any material, then if your properties are within a particular range, then you can accept those particular components. Another thing we have seen that what are the ways you can spend the money onto the component. That means cost versus performance was one of the criteria. So, here we have seen that you have to always stay into this leading edge, so that you can get more amount of performance compared to the cost and time you are spending into the getting system more ready. Then we have seen that we have to also focus not only cost and time, but we have to also finalize that which is the direction or which is the error which is important to remove or which is important to minimize. So, there are many errors, but some errors can be neglected which may not play important role during the fabrication or after fabrication. So, you pay more attention to the sensitive direction where your machine stiffness should be very high. Now, machining error generating processes. So, what is happening here, that first we have to identify the what are the sources of error, right. So, mostly sources of error are geometrical errors, and another is the cutting process error, drive error and the environmental error. What is the geometric error? So, geometric errors are mostly related to the structure of the machine, and it is mostly related to the machine tool. And cutting is that when you operate a machine, at that time you are end up with some type of cutting operation. So, your machine is in dynamic condition. Now, there are forces, there are acceleration, deceleration of the cutting tool in different motion, and then there are high heat generation. So, those things create some problem in the error. And then there are drives. So, drives means the table and your cutting tool which is moving up and down. So, those are called drives which move the slides and all the things. Environment, mostly it is related to temperature variation, humidity variation, and what things are located here, climate conditions. So, those things are related to this. So, these are the different sources of errors. Now, second is the mechanical system, that how these thing errors are affected in this direction. So, geometrical error are mostly related to the machine. So, this is the machine tool. What machine tool consists of? Machine tool consists of the table, spindle and the structure in this case. So, geometrical error are mostly connected with these particular things, because these are the table and the structure is always a stationary structure. So, if you are not getting a orthogonality between x, y and z direction, then you are end up with a some type of problem. So, these are what is required in this particular direction, right. All the things should be perpendicular to each other. So, if those things are not there, there are some other problems, then you are end up with some geometrical errors. What are the other components here? So, another one is the workpiece, because we know that machine tool is a standalone component, but there are two other things which we are adding into that depending on the selection of the machining operations. One is the workpiece, so that we are adding because we want to shape this particular thing. And why we are shaping that? We need a tool also, because the tool and workpiece, these both things are the selection based, and depending on the what is the specification of your machine tool, and these things are already inbuilt into the machine tool. So, cutting tool, cutting error, drive error, environmental error, that is directly connected with this also, and it may be connected with this also. So, these are the error sources. Where this error will occur, those things are these, because in the mechanical system this is the only things which are standard available. Now, if you add some camera or you add some microscope or you add some force sensor, those things are actually the supplementary things, but that cannot be considered during this particular error generation mechanism. Then error generating processes, what are these things? So, this is the static deformation, because in static deformation what happens that if you are not doing any machining operation or anything, because of the aging of this machine tool, then what happens, there is a static deformation in the structure, static deformation in the table also. In that way you are end up with some type of problems. Then dynamic deformation, that when your machine is in operation, you are cutting a workpiece by a tool and then it is in dynamic situation. So, now forces occurs, vibration occurs, and how your machine tool will tackle those type of dynamic situation, that everything depends on what is the error during the dynamic deformation. Thermal deformation, because thermal deformation occurs without operating machine or with operating machine. If it is operating the machine, then heat generation will be very high, because you are cutting a one material in by a friction or shear force, and that will increase the temperature at the cutting zone, and that temperature will propagate through the different components. Other than that, once you cut the material, chip also carries some temperature, and that when chip is falling at that particular location also temperature will be very high. So, you have to identify the thermal deformation or the higher temperature zone, and you have to insulate or the isolate those particular things, so that the temperature will not be propagated inside the system. Rotation accuracy, because that is related to spindle mostly, because when you rotate a spindle, mostly it should be in the eccentric with the spindle housing. If it is not like that, then what happens, there is a run out, dynamic run out is there, then static run out is there. So, those particular things will create a problem and it will generate some error during the process. Guiding accuracy is mostly related to the motion of the tool workpiece, that is by means of a table, because table workpiece is loaded on the table and the tool is loaded on the z axis. There is also guiding system which is moving your tool up and down. So, that is called z axis. So, their accuracy is also important, because all three axes should be perpendicular to each other as close as possible. So, that is also one of the source of errors. Dynamic movement error. So, when you are this is dynamic deformation that is in operation, and this dynamic movement error, that when you are doing machining and you are moving your workpiece from one location to another location. So, this is your tool, this is your workpiece, and this is your tool, and tool is penetrating inside the workpiece, and then you are moving to cut down this much amount of material, right. So, when you are moving, at that time if there is some problem with a guiding accuracy, that your all the three axes are not perpendicular to each other, at that time your material removal rate little bit higher or lower, depending on the angle at which your x, y and z axes are deviated. So, depending on that you will get a dynamic movement error, and that movement error will directly affect the life of your cutting tool and the quality of the workpiece which you are getting. Either it will be rejected or you have to do some rework to get that thing correct. Then the tool wear is also one of the things, because you cannot avoid the tool wear, but you can actually minimize the tool wear by setting a optimized parameter for this particular machine tool. So, in that way these are the different error generating processes, and what you are finally getting, what is our objective, that we should get a very high contour accuracy. Contour accuracy, that means suppose you want to get a circular component or it is a cylindrical component. So, it should be a cylinder only, it should not be some type of cone or positive way or the negative way. So, that is called contour accuracy. Surface roughness is important, because we have seen that we have different criteria for acceptance of the component, because error cannot be we cannot produce a perfect part. So, contour shape was one of the things, surface roughness was the another thing, and dimensional accuracy, that is how much, what is the tolerance level within that part. So, here we are not talking about the material properties, because that is another criteria not connected with the machine tool. So, here what we have to do, that first we have to find out that what is the problem in our part. Suppose you are not getting a surface roughness is not exactly the requirement. You are getting a contour is also okay, dimensionals are also acceptable. So, first if you are getting a surface roughness, then you have to actually go back side. So, which parameter is affecting the surface roughness? So, you have to go in this direction. So, suppose your tool is worn and still you are going continuing that particular machining operation, then there is a chance that tool wear is a one of the things which is creating a rough surface. Then once it is identified it is a tool wear, then go to this back side again, then which is the mechanical system which is creating a tool wear. So, here one is the tool which is directly connected, another is the workpiece also there, because if the workpiece is very hard and you are putting a speed, feed and depth of cut. So, these are the parameter, speed, feed and depth of cut. You are selecting a very aggressive value of this, then what happens, your tool wear will be very high. And machine tool, what we are doing, we are directly connected with this thing. So, again you have to identify out of these three options that which one is responsible for the tool wear. Once you identify that thing, suppose all the three are playing important role, then you have to find out that which one is more. Then if it is a machine tool, by speed, feed and depth of cut setting, you can do some changes there. If everything is fine, there may be a chance of a geometric error. So, then you can actually back calculate in this direction and find out what is the source of error, and then you spend time and cost for correcting this particular error source. Now, geometric errors on the machines. Now, these are the two configuration of the machine. So, this first one is the 3 axis machine and this one is the 5 axis machine. So, why 3 axis? Because now we can move table workpiece in x direction, y direction here and z direction here. Additional 2 axis here are the, one is the a axis. A axis means the rotation around the x axis, and the c axis, suppose you want to rotate your workpiece, not the tool. Tool rotation is already there, but when you want to rotate your workpiece, then what you have to do? You have to put another motor for rotation of that, because we know that this particular rotation is along the axis of the z. So, that is why it is called c axis. Now, still there is one axis left, that is called y axis. If you are putting one more motor and if you swing this particular whole stage, then what you are telling, that you are actually moving or tilting this particular table, that is in this direction. So, that is called b axis. So, depending on the requirement, you can actually design a micro machining center with a different axis freedoms. So, accurate part can only be achieved by a control or the deterministic manufacturing processes. Now, what does it mean? That first thing is the control. How you can control your thing? That suppose you have one machine and you have lot of feedback controllers. So, if you are moving from one location to another location, it is perfectly telling that your tool is moved from this to this location. So, this is your tool and it is moving from here to here. So, those are called the feedback controllers. Feedback controllers. So, what are those things? Those are the encoders, right. So, rotary encoders are there, that will find out the rotation of how many rotations are there depending on what is the translation. Linear encoders are also there. So, that will directly calculate the linear motion of that. So, those are called the feedback controllers. So, by feedback controller you can actually control your process, even if you have some type of backlash within the drive or something, then these particular encoders will take care about these particular problems. Another thing is the deterministic manufacturing process. Deterministic manufacturing process, that suppose you are setting a parameter for a, suppose you have a 3 component, that is a depth of cut, then RPM of tool and feed rate, right, and you have a one material or the workpiece and plus tool, you have selected one particular thing and you are getting one component out of this machine component, machine component. So, first experiment you are doing this thing, this is experiment number 1. You are doing experiment number 2 again. with the same parameter, and if you are getting the same thing here again, then that means it is called the deterministic manufacturing. That means you are not changing any parameter of the machine tool or the workpiece or tool combination every time you are getting a same component, that means your process is deterministic. So, in that case, if you are not putting any control or feedback controller, still your machine in such a condition that is always give a accurate part. Accurate part means within the acceptable limit. Right. So, we can tell that geometric accuracy of the part can be achieved either by a feedback loop through the part metrology. So, this is the feedback loop. Now, if you see, so there are many different components available. This is the tool is available here and the workpiece is here. So, these are the main things which is connecting the all the thing. So, now spindle is there. So, spindle, if you have put a variable frequency drive, you can get the feedback from the spindle RPM also. How much is the RPM of the spindle during actual operation? These are the movement in the Z direction, that is the in Z guide way. If you are putting a optical encoder here, linear encoder, then it will give you a signal of that thing, that how much is the movement in this direction. X axis drive is available, then there is a y axis drive. So, this particular movement will tell you the what is the actual position of your workpiece on a machine tool. Depending on that, there are different construction part is also available. So, this is the construction loop or the structural loop through which you can get the thing. So, if you have a very good feedback control, then you can get the geometrically correct component, or if that is the case, then another way you can get by calibrated machine tool. Calibrated, that means you know that if you have machine a component, that we have seen in earlier slide, that if you machine a component with a fixed parameter, you continue with the fixed parameter and every time you are getting the same component, that means your machine is calibrated. You do not have so much of deviation which will reject the part, or it will which will deviate the part even if you have all the input conditions are constant. So, that is the way, if both the things are there, it is a more perfect, much better than anything else, because you are getting a feedback also through the metrology part. Metrology part, that means you can measure the surface roughness also in that. If you have a roughness tester located here, if you have camera here directly, you can actually analyze the tool wear also, what is the parts geometry. So, these are called the metrology instrument, which will help you to monitor the machine tool as well as workpiece and the tool, even when it is in motion or when it is in machining condition. So, if both the things are much preferred, but if one of them is absent, then you have to rely completely on the other component. You have to make that particular things very strong, so that you can get the required geometrical accuracy into parts. Now, sources of geometry error. So, first let us take the geometric error, that means what are the sources of error in the XYZ direction or the movement of the axis only. Let us not go to the other way in the tool side or the workpiece side. So, accuracy of the machine tool is affected by many sources. So, if you see this particular thing, now you can understand that this should be the exactly straight line. If this is the straight line, this should be also perpendicular to this part, and this should be perpendicular to this one, and this should be perpendicular to this one. So, this should be the actual condition, but what happens that you have a external vibration, distortion and foundation problem. So, your base or the foundation is little bit skewed away, and that is the problem, that because of this deformation of this foundation, even if this all the three this thing and these things are right angle to each other, but because of this problem, what happened that this whole thing will move in the other direction. So, this whole thing will move in this direction now, even if it has contained a 90-degree part. So, this is also 90 degree, this is 90 degree, this is 90 degree, but this particular line is moved from this to this at one particular angle. So, whole thing is distorted. Now, there is a thermal fluctuation. So, if this particular thing is perfectly correct, now this is a straight line, there is no problem in that. So, whole thing is correct, and now thermal deformation occurs here. So, this will little bit bend, and this whole thing will also expand depending on the temperature effect or the temperature part. So, now this is completely something like that, and this is creating a problem. So, now these things are not right angle to each other, and that will create a problem. Then another thing, the motion and positioning error. Suppose this particular is the z axis, and z axis is right now it is little bit inclined here, because consider that your workpiece is very hard and you are moving this particular workpiece in this direction, correct, and your tool is not able to remove that material very high way. Then what happens, that your tool will bend here, and when tool will bend, it will create extra force here in this case, and few, because whatever you are looking at this particular deviation, this is not so high, but right now it is very exaggerated view of the small deformation, and that is what is important to understand here at this location. So, now coming to that down, now once it is in workpiece and this location, now consider this is all things are correct, no problem in that, and then you are doing a machining operation. So, machining operation also create a reaction forces. There are load because you have mounted a very heavy workpiece on the table, heavy vice is available which is fixing the component. Then because of that additional load, your foundation may get deformed at a micron level, and when you are getting a forces again propagate in this direction, this load and vibration will propagate in this direction, and then again it will close the loop, and because of this structural loop deflection, you are end up with the errors. So, what are the sources of errors? So, first is the kinematic errors, that means your axes are not right angle to each other, that is what is required. So, this thing should be orthogonal, that is the one thing. Second is thermomechanical error, the temperature effect because of the climate condition also and because of the machining operation. These are the two different sources through which you will get a temperature difference within the system. Loads means it is a stationary load also. Another thing is that when you do machining, there is a force also, and that will also consider as a dynamic load, which will also create a problem in the spindle system as well as in the other structural component. And the dynamic force, so this load is the stationary load, and this what force, dynamic force we are talking, these forces are the reaction force or some forces which occurs during machining operation. That means, when your machine is in running condition, at that time you will encounter these dynamic forces. So, these are the different forces which will create a problem in the geometry of the machine. So, first is the kinematic error. So, what is kinematic error? So, it is due to imperfect geometry, alignment and dimension of the machine component. So, suppose you have a complete structure of the machine, and if its geometry is imperfect, that means whatever dimension you are creating, that suppose you have a whatever this cantilever beam is, that it is square section or it is a circular section or it is other than any these two shapes, then its dimension should be perfectly within the allowance or within the tolerance limit. Alignment is also a problem, because we know that everything should be perfectly in alignment, so that your spindle axis is always in a vertical straight direction, not to the anything other than the straight thing. And the dimension of the machine component, because that will directly depend on this alignment, because if you are not exactly the dimension, you will not get the assembly problem, correct. And if there is a alignment problem, then you will not get the perfect combination of the different components. So, they are stable or changing slowly over time. Now, whatever these kinematic errors are there, sometimes what happens that initially you are not getting those things, but they are stable also, but as the time passes, what happens, you are doing machining with a different parameter setting, sometimes the forces are also very high. At that time, what happens, over the time this will start playing important role. So, that is because of the due to the foundation drift. What is the drift? So, drift is a deviation due to age. That means, whatever is this deformation due to age, or we can say it deformation with respect to time. If your machine is very old, then you will get a foundation drift. So, foundation drift means foundation is never in motion. So, it is always a stationary part, but because of this many things you are doing on the foundation, machining is there, you are mounting a very heavy vise or heavy workpiece on the top, then removing it again you are mounting. So, those things are playing important role in the study or the status of the foundation, what is the current status of the foundation. And wear or the material aging, because all the materials whatever you are using in the construction of the machine tool, it may get wear because of the aging. Aging means as with respect to time you are getting these materials in a very unstable condition. So, you may get some type of kinematic errors after a long time, and also by collision, because we know that when you do machining at a very high rate. Now, suppose your cutting tool is here and your workpiece is here at this location, and you want to remove these whole things. So, you start with the cutting tool here, and then right now you are moving from here to here, there is no any type of machining. So, it is called free machining. So, free machining and as soon as it is touching this particular part, then it will do actual machining. So, from here to here, as soon as it is coming into contact, you will get a very high force, in sudden highest force jumping in there. So, you have a spindle system here. So, this spindle system will, this particular force will be in this direction. So, your spindle will try to move in this direction. So, after your whole thing is moved here, and now you want to cut a under depth here. So, now your location of the cutting tool is here. Again you have one free time here, or the free machining here, or air cutting. So, here no force, and then you are suddenly striking this location, and your spindle system is here. At that time you are cutting in this direction, then your forces will be in this direction. So, if you move like here and there many times, because one day you are supposed doing such type of machining in 10 parts or 100 parts, every time this will be also considered as a collision. So, these particular small things also play important role in the maintaining or the stabilizing these particular kinematic errors. Then thermomechanical errors. So, what are the thermomechanical? The internal and external heat sources in the machine may lead to thermomechanical deformation of machine component, and then it leads to the kinematic error, because we have seen that we have a full construction here, that is in x, y and z direction. Right. So, this is the workpiece, this is the tool, this is the construction. Now, because of this temperature difference, what will happen? This particular thing has some coefficient of alpha here, this one has one thermal coefficient alpha, this one also, and every component has a different thermal coefficient. Coefficient of thermal expansion. Correct. So, if the materials are different, then all materials have different coefficient of thermal expansion, and depending on the temperature variation, your part will expand or contract differently. So, at the end, what are the location, it will create a problem. So, these are the location where it may create a problem, because it may bend in right side or the left side or right side, then your total geometric stability will be reduced. So, now let us see one video here, where it is showing that how this particular thing works. So, this is the company Okuma, they are making this particular system for temperature thermofluency concept, that is what we are looking at right now. So, what is this thing, that you can actually control the deformation within a 0.1 micron control. So, if your tool is deviating from one within a 0.1 micron, then you can actually control within that part. Intelligent machine construction. So, construction also play important role. If it is a symmetric structure, then the deformation will be symmetric, your tool will always be in the center. So, temperature equalization is important because whatever is the ambient temperature condition, your machine will actually respond to that temperature deformation. So, this is first thing that how machine will take care of. So, this is the installation space of the machine and this is the temperature variation. Now, if you see this particular thing, your temperature of the whole machine is within a particular zone. If there is, you will not find any orange spot or the red spot. So, this is the external. When you are changing the temperature of the climate, still your machine is in the same temperature. Machine adapts to the ambient temperature changes. Intelligent machine construction. So, how your machine you are constructing, that is important here. Right. If you see this thing, whole thing is at the, if you consider this, you draw one particular line from here, if you see this, both the things are symmetric in this case. What is the advantage? That now if even if there is a thermal deformation or the thermal expansion, this particular thing will expand in all the directions. So, your whatever is the location of this particular spindle, it will not be changed. So, that is the advantage of a thermal symmetric structure. Right. So, these ribs are important. Now, see the temperature is moving up here, but still you are in the same direction, thermally symmetric structure. And this is the box built structure. So, this whole thing is not a solid structure. Now, if you see from the cross section, you will find lot of ribs. So, this will help in dissipation of the temperature, because we know that now area increases here in this case, and that is the reason you can actually do a predictable deformation here. So, whatever deformation you can predict it. And this is thermal insulation. What is the importance of thermal insulation? That when you are doing machining, there is a heat generation, some heat will go to the right. So, this is the chip which are falling here in this location, and this is the temperature zone, high temperature zone. So, you are end up with this temperature. What you have to do? You have to provide one insulation here. So, chip will not be created any problem in the heating of the different component of the machine tool. And then this is the last one, this is the 0.1 micron deformation control. So, here what you need sensors which will sense the temperature variation. So, right now this is your target position, but it is in ambient temperature. Now, suppose you have a variation in the temperature, and because of that what is happening here, that your target is little bit shifted here, that is up to what 0.1 micron, that is called 100 nanometer. So, what this machine does, that it has a temperature sensor here. So, that temperature sensor will find out this particular temperature sensor spindle operation data. It will do calculation of the displacement here, that how much is the displacement because of the temperature variation. So, that displacement will directly do a compensation signal, and that will go to the axis control. And once you can get this thing, again it will calculate the original location, and then you can do the machining. So, there are lot of advantage of doing these particular things, because you can actually reduce the total variable time. So, here if it is without this thermofluidity concept, then you have to measure temperature throughout the operation. Here you do first measurement, then it will take care about everything. You have to do one thing only here. Then this is the no compensation. Within the compensation, you can actually maintain the x axis displacement within one range, and you cannot get any type of stability problem here. So, these are the different advantage of using this particular systems. So, let me finish this lecture here, and we will continue this lecture or this topic further in the next class. Thank you.